In the most ordinary moments, when nothing seems to be happening at all, something remarkable is quietly at work. Objects remain solid beneath your weight. Sounds travel through air. Heat drifts from warmer places to cooler ones. Light arrives from distant sources with dependable speed. None of this requires attention to continue. It happens whether it is noticed or not. Beneath every calm surface and familiar motion, the universe is following rules. Not rules written down or enforced, but patterns that repeat with such reliability that they can be trusted. Patterns that allow stars to shine for billions of years, that let atoms hold together, that cause time to move forward rather than backward. Patterns so steady that entire technologies, entire civilizations, quietly depend on them without ever needing to name them. Welcome to the Sleepy Scientist. If slow, thoughtful journeys through ideas like this help you unwind, you're very welcome to subscribe and join these quiet explorations. And if you feel like it, you're always invited to share where in the world you're listening from tonight. It's comforting to remember how far these thoughts travel. For centuries, humans have tried to describe these patterns, not all at once, and not perfectly. First through observation, then through careful measurement, and eventually through laws, statements that say, in effect, when the universe is placed in this situation, it behaves in that way. Not because it must, but because it always has. Some of these laws feel intuitive. Objects fall when released. Heat spreads. Motion continues unless something interferes. Others are less comfortable. Time stretches. Certainty dissolves at small scales. Space itself can bend. And yet even the strangest discoveries share something in common. They follow rules, quiet ones, consistent ones. Modern science has revealed that these laws operate across an enormous range of scales, from the motion of planets to the vibration of atoms, from the slow cooling of a cup of tea to the life cycle of galaxies. And while the laws themselves are precise, our understanding of them has always been incomplete. Each generation refines the picture, discovering not only new rules, but the limits of old ones. Tonight's journey moves slowly through those laws, not as equations or technical proofs, but as ideas, as descriptions of how the universe behaves when left to itself. What will be explored is not everything physics knows, but the quiet structure beneath it. The rules that make reality predictable enough to feel safe and strange enough to remain interesting. There is no need to follow every detail. Nothing here needs to be memorized. These laws have been operating long before anyone named them, and they will continue whether or not they are understood. This is simply an invitation to notice them, to let them pass by gently, like background music to a much larger story. Settle in. Let the universe behave as it always has, slowly, reliably, and without asking for attention. Nothing about the universe suggests it should behave the same way twice. At first glance, reality looks improvised. Clouds form and dissolve without obvious instruction. Flames flicker unpredictably. Leaves fall in different paths every time they are released. And yet, beneath that surface variation, something remarkably steady is taking place. When the same conditions repeat, the outcomes quietly repeat as well. Objects fall downward rather than sideways. Warm things cool when placed in colder surroundings. Light travels outward instead of lingering in place. Even chaos, it turns out, has habits. This quiet repeatability is the reason science exists at all. If nature behaved differently every time, observation would be meaningless. Memory would offer no guidance. Prediction would be impossible. But the universe does repeat itself. Not perfectly, and not in detail, but in structure. When similar situations arise, they unfold in familiar ways. This is not because the universe is simple, but because it is consistent. Physicists use the word law to describe this consistency. though the word can be misleading. A law of physics is not a command issued to reality. Nothing is being ordered to behave. Instead, a law is a summary. A carefully worded statement that says, whenever the universe finds itself arranged like this, it behaves like that. No intention is assumed. No enforcement is required. The regularity is simply observed, tested, and described. This idea feels natural now, but it took a long time to recognize. Long before laboratories or instruments, early observers noticed that the sky behaved with rhythm. The sun rose and set. The moon cycled through phases. Certain stars returned to the same positions year after year. These patterns were reliable enough to build calendars, track seasons, and guide travel. In ancient Greece, thinkers began to suspect that these repetitions were not coincidences, but expressions of deeper order. Motion, change, and rest were not random. They followed tendencies. Aristotle believed that objects had natural behaviors. Stones fell because they belonged to the earth. Flames rose because they belonged to the heavens. While much of this reasoning would later be revised, the instinct behind it was crucial. Nature was not arbitrary. It behaved in ways that could be understood, even if the understanding was incomplete. As centuries passed, this belief in regularity slowly sharpened. Observations became measurements. Descriptions became comparisons. By the time careful astronomical records were being kept in the early modern period, patterns were no longer just noticed, they were quantified. Planets did not wander aimlessly. Their paths could be traced, their positions predicted. Motion itself seemed to follow rules. What is remarkable is not that these early ideas were sometimes wrong, but that they worked at all. Even imperfect theories could function because they were anchored to something real. The universe was offering repeated behavior, and humans were learning how to listen. This is why physicists are careful with the language of laws. A law is not declared and then obeyed. It is inferred and then tested. If observations stop matching the description, the law does not punish the universe. The law is revised. This has happened many times. Each revision did not erase the old understanding, but placed boundaries around it, showing where it worked and where it quietly failed. The reason this process works is that nature does not reinvent itself from moment to moment. There is noise, variation, and complexity, but there is also structure beneath it. Drop a stone today or tomorrow and it behaves the same way. Heat a gas and its pressure changes in a predictable direction. Shine light through a narrow opening and it spreads in a familiar pattern. These are not coincidences stacked on top of one another. They are expressions of stability. Large scientific bodies like national observatories and international physics institutions rely on this stability every day. Satellites remain in orbit because gravitational behavior is consistent. Power grids function because electrical relationships do not drift overnight. Medical imaging works because radiation interacts with matter in repeatable ways. The entire technological world is balanced on the assumption that the universe will behave tomorrow the way it behaved yesterday. There is a quiet comfort in that. At the same time, regularity does not mean rigidity. Patterns allow variation within boundaries. No two snowflakes are identical, yet they all follow the same underlying rules of crystallization. No two storms are the same, yet atmospheric motion obeys the same physical principles each time. Even biological evolution depends on consistency. Mutations only matter because inheritance follows rules. Change is meaningful because stability exists underneath it. This balance between repetition and variation is what makes laws useful without making reality dull. It is also why physicists care so deeply about finding the simplest possible descriptions. When many different phenomena turn out to follow the same pattern, something fundamental is being revealed. The fewer assumptions needed to explain behavior, the more likely it is that a genuine regularity is being captured rather than a coincidence dressed up as a rule. Over time, some laws have proven astonishingly robust. They hold across continents, centuries, and scales. Others work beautifully in familiar conditions but quietly fail when pushed too far. This is not a flaw. It is information. Each limit reveals something new about where one pattern gives way to another. What matters here is not memorizing any specific law, but recognizing why laws exist at all. They are not artifacts of human thinking imposed on a chaotic universe. They are reflections of something the universe is already doing. Science, at its calmest, is simply the practice of noticing those reflections with care. This chapter serves as the ground beneath everything that follows. Before forces, before energy, before space and time become strange, there must be trust that nature behaves with continuity. That trust is not philosophical optimism. It is earned through repetition, through the quiet confirmation that similar causes tend to produce similar effects. From here, attention can narrow. Patterns are broad, but they become most visible when something moves. Motion is where regularity first becomes measurable. Positions change, speeds vary, paths curve, and yet, even here, order remains. The universe moves, and in its movement, it reveals rules. Once patterns are noticed, the next question arrives naturally. If the universe behaves consistently, how does that consistency show itself when things begin to move? Motion is where regularity becomes visible. A stationary world would offer little to study, but a moving one leaves trails, changes positions, and reveals relationships. Something shifts, and something else responds. Over time, those responses begin to repeat. Push gently, and an object drifts. Push harder, and it speeds up. Stop pushing, and eventually it slows again. These simple observations form the first solid bridge between abstract patterns and measurable reality. By the 17th century, this bridge had become sturdy enough to support a new way of thinking. Motion was no longer described in terms of purpose or natural inclination, but through clear relationships. How fast something moves, how quickly that motion changes, what happens when objects interact. This approach is now called classical mechanics, and it rests on three foundational ideas often known as the laws of motion. They are not complicated statements, but they are profound ones. Together they describe how objects behave when forces act on them, and just as importantly, what happens when they do not. The first idea is inertia. Left alone, an object does not seek rest or motion. It simply continues as it is. Something already moving keeps moving in the same direction at the same speed. Something at rest remains still. This feels almost obvious today, but for much of history it seemed wrong. Everyday experience suggests that motion fades naturally. A sliding book stops. A rolling ball slows. But this is not because motion runs out. It is because the world is full of subtle interference. Friction from surfaces. Resistance from air. Tiny forces constantly working to change motion. Remove those influences and the picture changes. In the near vacuum of space, objects glide for astonishing distances without slowing. Space agencies rely on this every day. Once a spacecraft is set on its path, very little effort is required to keep it moving. Inertia does the work quietly and reliably. The second idea describes how motion changes. When something does speed up, slow down, or change direction, it does so because of a force. The greater the force applied, the greater the change in motion, and the more massive an object is, the more it resists that change. This relationship is often summarized by an equation, which in spoken form becomes force equals mass multiplied by acceleration. It sounds technical, but its meaning is familiar. It is easier to push an empty shopping cart than a full one. It takes more effort to stop a moving car than a bicycle. Mass measures resistance to change, and force is what overcomes it. Acceleration here does not only mean speeding up. Turning a corner is also acceleration. So is slowing down. Any change in velocity, whether in speed or direction, counts. This explains why sharp turns feel more dramatic at higher speeds. The motion is changing more rapidly, and the body notices. The third idea completes the picture by focusing on interaction. Forces do not appear alone. Whenever one object pushes on another, the second pushes back with equal strength in the opposite direction. This is not retaliation. It is symmetry. When feet press against the ground presses back, allowing walking to happen at all. When a swimmer pushes water backward, the water pushes the swimmer forward. Even sitting still involves a balance of forces, with gravity pulling downward and the surface beneath providing support. This principle explains why rockets work in empty space. There is no air to push against, but there does not need to be. The rocket pushes exhaust gases backward, and the gases push the rocket forward. Motion emerges from interaction, not environment. Together, these ideas form a remarkably complete description of everyday motion. They govern falling objects, spinning wheels, swinging pendulums, and orbiting satellites. Engineers still rely on them daily. Bridges are designed using these principles. Vehicles are tested against them. Buildings stand because the forces within them balance predictably. What makes these laws especially powerful is their range. They apply to objects weighing a few grams and to structures weighing thousands of tons. They describe motion at walking pace and motion at thousands of meters per second. Within their proper domain, they are astonishingly accurate. Scientific institutions across the world use these relationships constantly. Aerospace agencies calculate trajectories using them. Mechanical engineers test stress and strain through them. Even sports science relies on them to analyze movement and reduce injury. They form a shared language between observation and application. There is also something quietly elegant about how little they require. No assumptions about purpose, no need for hidden intentions, just mass, motion, and interaction. The universe, in this view, does not push things toward goals. It simply responds to forces with consistency. And yet, these laws are not the full story. They describe how motion behaves when forces act, but they do not explain where those forces come from. They can tell how fast something accelerates, but not why energy is conserved. They can predict paths, but not why heat spreads or why time seems to move in only one direction. Even within motion itself, they begin to falter when speeds approach that of light, or when objects shrink to atomic scales. This is not a failure. It is a clue. The laws of motion provide a solid foundation, but foundations exist to support further structure. Motion reveals patterns, but change involves more than movement alone. To understand why systems evolve, why some processes reverse and others do not, and why the universe behaves differently at different scales, something deeper is required. For now, what matters is that motion is not mysterious. It follows rules that are calm, consistent, and reliable. These rules have been tested for centuries and continue to work wherever everyday experience applies. They remind us that beneath the apparent complexity of the world there is a steady rhythm. Push, and something responds. Stop pushing, and it continues on its way. The universe moves, and in that movement, it remains remarkably predictable. Once motion is understood as something that responds predictably to forces, another quiet question begins to surface. When objects move, what exactly is being carried along with that motion? What is it that persists, even as directions change and interactions unfold? Physicists call this quantity momentum. In its simplest sense, momentum is mass in motion. It captures not just how fast something is moving, but how much substance is moving along with it. A slowly rolling truck and a rapidly thrown pebble may share a speed for an instant, but their momentum is vastly different. One is easy to stop. The other demands planning, distance, and strong brakes. Momentum matters because it behaves in a surprisingly disciplined way. In isolated systems where outside influences are negligible, the total momentum does not change. It can move from one object to another, split, combine, or reverse direction, but the overall amount remains the same. This principle is known as conservation of momentum, and it turns out to be one of the most dependable regularities ever observed. It appears everywhere once attention is drawn to it. Take something as ordinary as walking. With each step, a foot presses backward against the ground. In response, the ground pushes forward with equal strength. Momentum is exchanged. The body moves ahead, not because the ground cooperates, but because momentum must be conserved. Walking is not a conquest of the earth, it is a negotiation with it. The same exchange happens in water. A swimmer pushes fluid backward and glides forward as momentum shifts from body to surrounding liquid. In air, birds do the same with wings. Motion emerges not from effort alone, but from the careful redirection of momentum. More dramatic examples reveal the principle even more clearly. When a firearm is discharged, the projectile surges forward, and the firearm itself recoils backward. The backward motion is not an afterthought. It is required. The forward momentum of the projectile must be balanced by an equal amount in the opposite direction. The heavier the projectile or the faster it moves, the stronger the recoil must be. This same logic governs rocket propulsion. Long before spacecraft existed, the principle was already at work. Rockets move forward because exhaust gases are expelled backward. There is no need for air or external surfaces. Momentum alone is enough. Space agencies rely on this fact constantly. Maneuvering satellites, adjusting orbits, and traveling between planets all depend on carefully accounting for momentum transfers. Even collisions, which often feel chaotic, obey this rule with precision. When two objects collide, their individual momenta change, but the total remains constant. In gentle collisions, objects may bounce apart. In others, they may stick together and move as one. The details differ, but the accounting always balances. Momentum is redistributed, not destroyed. This reliability has deep consequences. Because momentum is conserved, large systems tend to resist sudden change. Planets remain in stable orbits because their momentum carries them forward even as gravity gently curves their paths. Stars within galaxies continue their slow rotations. Entire cosmic structures maintain coherence over billions of years because momentum does not simply fade away. Without this conservation, the universe would be wildly unstable. Motion could vanish without explanation, structures would unravel, predictability would disappear. Instead, motion persists, transferred patiently from place to place, scale to scale. Scientists working in fields ranging from astrophysics to particle physics rely on this principle constantly. Observatories analyzing distant collisions between galaxies use momentum conservation to infer unseen matter. Particle accelerators track tiny fragments created in high-energy impacts, reconstructing what must have occurred by ensuring momentum balances in every direction. Even when something cannot be seen directly, its momentum leaves a trace. There is a quiet elegance to this. Momentum does not care about materials, shapes, or intentions. It applies equally to dust grains and mountain ranges, to electrons and planets. It is indifferent to complexity. All that matters is mass and motion. Yet momentum alone does not explain everything. Consider two identical balls rolling across a surface. Both carry momentum. Over time, both slow down. Momentum seems to disappear, But it has not vanished. It has been transferred little by little into the surface, into the air, into microscopic vibrations and heat. Momentum conservation still holds, but it becomes harder to track as it spreads across many particles. This spreading hints at something broader. Momentum tells how emotion is distributed, but it does not fully capture the capacity for change. It describes direction and persistence, but not usefulness. A slowly drifting asteroid and a rapidly spinning turbine may have comparable momentum under certain conditions, yet their ability to do work differs dramatically. This is where momentum begins to share the stage with a deeper accounting principle. Physicists notice that while momentum explains stability and balance, another quantity is needed to describe transformation. To understand why machines operate, why heat flows, why motion can be harnessed and redirected, something more general is required. Momentum ensures fairness in interaction. Something else governs possibility. Still, momentum remains foundational. It explains why motion feels stubborn, why stopping a heavy vehicle requires distance, why sudden changes feel uncomfortable, why balance matters. It underlies every act of movement, whether deliberate or accidental. Even standing upright involves countless small momentum exchanges as the body continually adjusts to remain stable. There's also a subtle comfort in knowing that motion is not fragile. Once present, it does not simply evaporate. It must go somewhere. The universe keeps careful track, even when the bookkeeping becomes complex. In this sense, conservation of momentum contributes to the universe's overall calm. It prevents sudden surprises. It ensures continuity. Change happens, but not without accounting. As understanding deepens, this idea of conservation begins to appear again and again, wearing different names, applying to different quantities. Momentum is one expression of a larger pattern, a hint that the universe prefers balance over loss, redistribution over disappearance. From here, attention naturally broadens, motion is conserved, direction is accounted for. But what about the ability to cause change itself? What about the capacity that drives motion, fuels reactions and flows invisibly through every process? To answer that, physics turns to a concept even more universal than momentum, one that does not depend on direction at all, yet governs nearly everything that happens. Momentum keeps careful track of motion, making sure nothing simply disappears. But motion alone does not tell the whole story of change. A moving object can collide and come to rest, yet something unmistakable has happened. Heat is felt. Sounds are produced. Materials warm, bend or transform. The motion may be gone, but its effect remain. To understand this broader picture, physics turns to a concept that is less visible than motion, but far more universal. Energy is best understood as the capacity for change. It is not a substance that can be held, and it is not a single thing that looks the same in every situation. Instead, energy appears in many forms, each connected by a simple idea. If something can move, warm, stretch, glow, react, or transform, energy is involved. This idea took shape slowly. For a long time, heat and motion were thought to be entirely different phenomena. Warmth was treated as a fluid that flowed from one object to another. Motion was something mechanical and separate. What changed this view was careful measurement. In the 19th century, experiments began to reveal a deeper connection. One of the most important figures in this shift was James Joule. Through painstaking work, Joule showed that mechanical motion could reliably produce heat. Stirring water with paddles driven by falling weights caused the temperature of the water to rise. The amount of warming depended not on the material of the paddles, but on how much work was done. Motion was turning into heat in a predictable way. This was a quiet revelation. It suggested that heat was not a substance at all. but a form of energy associated with microscopic motion. The warmth of a cup of tea, the glow of heated metal, the friction felt when hands are rubbed together, all pointed to the same underlying process. Energy was changing form, not vanishing. From this insight emerged one of the most far-reaching principles in all of science. The total amount of energy in an isolated system remains constant. It can change form, move between objects, spread out, or become harder to detect, but it cannot be created from nothing or destroyed entirely. This is known as the law of conservation of energy. Its simplicity is deceptive. Energy appears in motion, which is often called kinetic energy. It appears stored in stretched springs, compressed gases, chemical bonds, and elevated objects. It appears as heat, light, electrical activity, and even mass itself. These forms look different, behave differently, and affect the senses in different ways. Yet careful accounting shows that they are interchangeable. A swinging pendulum illustrates this beautifully. At the highest point of its swing, the pendulum is momentarily still, yet energy is present, stored by its position in a gravitational field. As it descends, that stored energy becomes motion. At the lowest point, motion is greatest. As it rises again, motion fades and storage returns. The total never changes. It simply trades disguises. This trade happens everywhere. A car engine converts chemical energy stored in fuel into motion, heat, and sound. A power station turns motion into electricity. A light bulb converts electrical energy into light and warmth. Even the human body follows this pattern. Energy from food becomes movement, body heat, and the quiet work of maintaining life. Large scientific institutions depend on this principle constantly. Energy accounting allows engineers to design machines, predict efficiency, and avoid catastrophic failure. Climate scientists track energy flows through the atmosphere and oceans to understand warming trends. Astronomers study how stars shine by tracing the conversion of mass into radiant energy over billions of years. The reach of energy conservation is extraordinary. It applies at the scale of molecules and at the scale of galaxies. It holds in laboratories and in the depths of space. No confirmed experiment has ever shown a true violation. That said, energy does not always behave in ways that feel intuitive. Although energy is conserved, its usefulness is not. A moving object can do work. A warm object can heat its surroundings. But once energy spreads out, once it becomes thinly distributed among countless particles, it becomes difficult to gather again. The total remains the same, but its ability to produce noticeable change diminishes. This is why a cup of hot coffee cools down, but never spontaneously reheats itself by drawing warmth back from the room. The energy is still there, dispersed among air molecules and surfaces, but it has become too evenly spread to be useful in the original way. This distinction matters. Conservation tells us that nothing is lost. Experience tells us that something has changed irreversibly. Energy conservation also reshaped how physicists understood motion itself. Momentum tracks direction and balance. Energy tracks capacity. An object may carry little momentum but enormous energy, or vice versa. A spinning flywheel stores large amounts of energy without travelling anywhere. A slowly moving glacier carries tremendous momentum but changes energy only gradually. There is gentle humour in how stubborn energy can be. Try as machines might, they cannot cheat it. No engine can produce more energy than it consumes. No clever design escapes losses to heat. Efficiency can improve, but perfection remains unreachable. This is not due to poor engineering. It is a fundamental feature of reality. Even modern technologies bow to this rule. Batteries do not create energy, they store it. Solar panels do not generate energy from nothing. They convert radiant energy arriving from the sun. Nuclear reactors do not summon power from empty space. They rearrange matter in ways that release energy already present. This universality makes energy a powerful organizing idea. When something changes, energy is moved or transformed. When change stops, energy has settled into a form that resists further action. By following energy, physicists can often explain processes that appear unrelated on the surface. Yet conservation, while reassuring, leaves an important question unanswered. If energy is always preserved, why does the universe still seem to run down? Why do systems tend towards stillness and uniformity rather than spontaneous organization? Why does useful energy appear to fade even though none is lost? The answer lies not in how much energy exists, but in how it spreads. As energy flows from concentrated forms into dispersed ones, it becomes harder to direct. Motion turns into heat. Heat spreads into the environment. Differences even out. The universe remains energetically full, but increasingly uniform. This subtle shift does not violate conservation, it complements it. To understand why processes favour certain directions, why time seems to move forward, and why change often feels one way rather than reversible, physics must look beyond quantity alone. It must consider distribution, not just how much energy exists, but how it is arranged. That inquiry leads away from motion and toward heat, order, and the quiet rules that govern how energy spreads once it is free to roam. Energy never disappears, but it does not stay neatly where it began. Once this becomes clear, a deeper set of rules quietly comes into view. These rules do not describe how much energy exists, but how it moves, spreads, and settles. They explain why some changes feel natural and others never seem to happen at all. Together, they are known as the laws of thermodynamics. The first of these laws is a direct extension of what has already been seen. Energy is conserved. In any process, the total amount remains the same, even as it shifts form. Motion can become heat. Electrical energy can become light. Chemical energy can become movement. Nothing is lost. Nothing is created from nothing. The universe keeps perfect track. This principle was not obvious at first. During the early days of industrial machinery, engines were inefficient and unpredictable. Steam engines leaked energy everywhere, producing heat, noise, and motion in tangled proportions. Engineers struggled to understand why so much effort produced so little useful work. As measurements improved in the 19th century, a pattern emerged. No matter how an engine was built, the total energy going in always matched the total energy coming out, once every form was counted. This realization unified mechanics and heat under a single accounting system. Energy was not multiple things. It was one thing, wearing many disguises. The second law of thermodynamics addresses a subtler question. If energy is conserved, why does it seem to become less useful over time? This law states that energy tends to spread out. When left alone, differences in temperature smooth themselves away. Concentrated energy disperses, hot objects cool, cold objects warm. Over time, energy becomes more evenly distributed among available states. This tendency is captured by a concept called entropy. Entropy is often described as disorder, but this word can be misleading. A better way to think about entropy is as energy dispersal. When energy is concentrated in one place or one form, there are fewer ways it can be arranged. When it spreads out, there are vastly more possibilities. Imagine a drop of ink falling into a glass of water. At first, the ink is localized. Over time, it spreads until the color is uniform. The final state is not chaotic, it is stable. The same logic applies to energy. When heat spreads through a room, it does not create confusion. It creates balance. This explains why heat flows from warmer objects to cooler ones and not the reverse. When a hot cup is placed in a cool room, the energy in the cup has many more ways to spread into the surrounding air than to remain concentrated. The reverse process, where energy spontaneously gathers itself back into the cup, is not forbidden by conservation, but it is overwhelmingly unlikely. Physicists sometimes express this tendency with an equation, spoken aloud as the change in entropy equals the heat transferred divided by temperature. While the details are technical, the message is simple. Heat prefers to spread. Energy favours arrangements with more available possibilities. These insights emerged alongside the rise of steam engines and industrial machinery. Scientists like Sadi Carnot studied idealized engines to understand the limits of efficiency. His work showed that no engine could convert all incoming heat into useful work. Some energy would always be lost to the surroundings as heat. This was not due to poor design. It was a universal constraint. The second law places a ceiling on efficiency that no technology can exceed. It explains why perpetual motion machines of the second kind are impossible. Even perfect engineering cannot overcome the tendency of energy to disperse. Modern institutions continue to rely on these laws. Power plants are designed around thermodynamic limits. Refrigeration systems work by carefully managing energy flow, rather than eliminating entropy. Climate models track heat movement through the atmosphere and oceans using thermodynamic principles. From engines to ecosystems, these laws quietly govern what is possible. There is something almost gentle about the second law. It does not forbid activity. It allows stars to burn, weather to flow, and life to exist. But it insists that all activity leaves traces. Energy spreads, differences fade. Over time, concentrated sources run down. This does not mean the universe is rushing towards stillness. Locally, order can increase. Structures can form. Life can thrive. But this happens by exporting entropy elsewhere. A refrigerator keeps food cold by dumping heat into the room. A living cell maintains order by releasing energy into its surroundings. Balance is preserved globally even as complexity arises locally. This balance gives the universe a sense of direction. While many physical laws work the same forward and backward, thermodynamics does not. A shattered glass does not reassemble itself. Warm coffee does not reheat spontaneously. These asymmetries are not matters of preference. They reflect the statistical weight of possibilities. There are vastly more ways for energy to be spread out than concentrated. As a result, thermodynamics provides something rare in physics. It offers a reason why processes unfold in one temporal direction. Not because time itself pushes them forward, but because energy naturally explores the largest available space of arrangements. This is why thermodynamics is often linked to the experience of time. Memory depends on irreversible processes. Aging follows from gradual energy dispersal. Even the act of measuring leaves an energetic footprint. The laws of thermodynamics do not describe motion directly. They describe tendencies, preferences, the quiet bias of the universe toward equilibrium. And while energy conservation reassures that nothing is ever truly lost, thermodynamics explains why what remains feels different, why energy that was once concentrated and powerful becomes diffuse and gentle, why change has a direction even when the underlying rules remain symmetric. From here, the question shifts again. If energy dispersal gives processes a preferred direction, then perhaps time itself is not as neutral as it appears. Perhaps the flow of events is shaped not by clocks alone, but by the quiet, statistical pull of energy spreading into ever more possibilities. That possibility invites a closer look at why the universe seems to remember the past but never the future. By this point, a quiet imbalance has revealed itself. The laws that describe motion and energy work just as well forward as backward. A planet's path can be reversed on paper without contradiction. Collisions can be mathematically unwound. Yet lived experience stubbornly disagrees. Spilled milk does not leap back into its glass. Smoke does not retreat into a flame. Time, it seems, has a preferred direction. This direction is often called the arrow of time. The arrow does not come from clocks or calendars. It does not arise from motion itself. Instead, it emerges from the same tendency already encountered in thermodynamics. Energy spreads. Differences smooth out. Concentrated states dissolve into distributed ones. And once that spreading has occurred, returning to the original arrangement becomes unimaginably unlikely. This is what makes many processes irreversible. A glass shatters when dropped. The pieces scatter across the floor. In principle, the laws governing the atoms involved would allow the reverse sequence. The fragments could leap upward, reassemble mid-air, and settle gently onto the table. Nothing in classical mechanics forbids it. But the number of microscopic arrangements corresponding to a shattered glass is astronomically larger than the number corresponding to an intact one. The universe overwhelmingly prefers the former. Irreversibility then is not about impossibility. It is about probability. This insight reshaped how physicists thought about time. In the late 19th and early 20th centuries, scientists like Ludwig Boltzmann explored how large-scale behavior emerges from countless microscopic interactions. Boltzmann showed that when systems contain enormous numbers of particles, statistical tendencies dominate. The most probable state becomes the one observed. Time's arrow is simply the direction toward increasing probability. Entropy, understood as energy dispersal, increases because there are more ways for energy to be spread than concentrated. Once energy has dispersed, there are fewer paths back to the original configuration. Time's direction follows the slope of likelihood. This statistical view explains why irreversibility appears everywhere. Heat flows from warm to cool because there are vastly more microscopic arrangements corresponding to evenly distributed energy. Gases mix because separated states are rare compared to mixed ones. Even sound behaves this way. A sharp noise disperses into the environment, never gathering itself back into silence. Memory itself depends on this irreversibility. To remember something, a physical change must occur. Neurons shift, molecules rearrange, energy is expended. That change leaves a trace that points backward, not forward. There are memories of yesterday, but none of tomorrow, because memory formation relies on processes that increase entropy. Recording information always leaves an energetic footprint. Aging follows the same logic. Biological systems maintain order by exporting entropy to their surroundings. Over time, damage accumulates. Repair mechanisms lose efficiency. The arrow of time expresses itself as wear, not because life is poorly designed, but because maintaining structure requires continuous energy flow. When that flow falters, order slowly gives way. Causality, too, rests on this foundation. Causes precede effects because effects typically involve energy spreading into more possibilities. Lighting a match leads to a flame and heat dispersal. The reverse sequence would require energy to spontaneously reconcentrate into the match head. Again, not forbidden, but fantastically unlikely. What makes this especially intriguing is that most fundamental equations in physics do not care which way time points. The equations governing motion, electricity, and even quantum behavior often work equally well forward and backward. The arrow does not appear at the deepest mathematical level. It emerges when many components interact. Time, in this sense, is not imposed from outside. It is a collective phenomenon. This perspective has been tested and refined through experiments and observations across many fields. Statistical mechanics connects microscopic motion to macroscopic behavior. Information theory links entropy to uncertainty and knowledge. Cosmology traces how the universe began in an unusually low entropy state, allowing time's arrow to unfold on a cosmic scale. The fact that the early universe was highly ordered remains one of the most important clues in modern physics. It suggests that time's arrow is not eternal, but contingent. It exists because conditions once allowed it to exist. Since then, the universe has been gently, persistently exploring more probable arrangements. There is a subtle calm in this realization. Time is not rushing forward with intent. It is simply following the quiet slope laid out by statistics. Each moment flows into the next not because it must, but because there are more ways for it to do so. This also explains why time feels smooth and continuous. At microscopic scales, particles jitter and collide. But when averaged over vast numbers, their behavior produces a steady progression. Time becomes a reliable parameter not because it is fundamental, but because it is stable. Even the most precise clocks rely on irreversible processes. Atomic transitions emit energy. Signals propagate outward. Every tick involves change that cannot be undone without leaving further traces. Measuring time consumes time. And yet, despite its directionality, time does not exert force. It does not push objects along paths or bend trajectories. It provides a backdrop against which other influences operate. Motion happens within time, but it is shaped by forces. Once the arrow of time is understood as an emergent feature of energy dispersal, attention naturally shifts again. Motion and change unfold over time, but what guides their paths? What causes trajectories to curve, objects to attract, charges to repel? To answer that, physics turns from time's direction to the influences that act across space. Time provides direction, but it does not explain why paths bend or why motion curves instead of continuing endlessly in straight lines. Something else is at work, an influence that reaches across space, quietly shaping movement without ever needing contact. That influence is gravity. Gravity is the most familiar of all physical interactions, and yet it is also the most subtle. It cannot be switched off. It does not announce itself with sparks or sound. It simply acts, everywhere, all the time. Anything with mass attracts anything else with mass. No exceptions have ever been observed. This idea feels almost too simple, but its consequences are vast. On Earth, gravity reveals itself in the most ordinary ways. Objects fall when released. Rain returns to the ground. Feet stay planted rather than drifting away. These experiences are so constant that they fade into the background of awareness. Gravity becomes invisible precisely because it never takes a break. What makes gravity remarkable is not just that objects fall, but that they fall predictably. Drop a stone today or tomorrow, and its behavior is the same. Increase its height, and it takes longer to reach the ground. Release two objects of different mass, and ignoring air resistance, they fall together. This regularity hints at an underlying rule. In the 17th century, Isaac Newton gave that rule its first precise form. He proposed that gravity is a mutual attraction between masses. The greater the mass, the stronger the pull. The closer the objects, the stronger the interaction. This relationship applies equally to apples and planets. Newton's insight was not that gravity exists, but that the same gravity governing falling objects also governs celestial motion. The force that pulls an apple toward the ground is the same force that holds the moon in its orbit around Earth and guides planets around the sun. Planetary motion provided some of the clearest confirmation of this idea. Observations of planetary paths showed that planets do not move in perfect circles, but in elongated orbits. These motions could be predicted with extraordinary accuracy using Newton's gravitational framework. Once mass and distance were accounted for, trajectories unfolded exactly as expected. Astronomers quickly realized how powerful this was. By tracking motion alone, unseen masses could be inferred. Variations in planetary paths revealed the presence of additional bodies. Entire planets were discovered not by sight, but by gravitational influence. Something unseen was tugging, and motion revealed it. The reach of gravity extends far beyond our solar system. Stars orbit the centers of galaxies. Galaxies cluster together in vast cosmic webs. Even light, despite having no rest mass, follows curved paths when passing near massive objects. Observatories around the world have confirmed these effects by watching distant starlight bend around intervening galaxies, producing arcs and distortions that match gravitational predictions. Gravity also explains stability. Without it, matter would drift apart. Stars would not form. Planets would not gather. Atmospheres would escape into space. Gravity provides the gentle binding that allows structures to persist over immense spans of time. It is strong enough to shape the cosmos, yet weak enough to allow delicate balance. There is also a quiet democracy to gravity. It treats all mass equally. A feather and a hammer fall together in the absence of air. A mountain and a grain of sand both contribute to Earth's gravitational pull, even if one contribution is much smaller than the other. Gravity does not discriminate by composition or charge. Only mass matters. Scientific institutions rely on this predictability constantly. Space agencies calculate spacecraft trajectories years in advance, trusting gravitational interactions to remain stable. Astronomers model the evolution of galaxies over billions of years using the same principles. Even global positioning systems depend on precise gravitational calculations to maintain accuracy. Yet gravity remains slightly mysterious. Unlike other influences, gravity cannot be blocked or shielded. There is no known material that stops it. It passes effortlessly through matter, acting regardless of obstacles. This universality sets it apart and raises deeper questions about how it operates. What is clear is that gravity does not require contact. Objects influence one another across empty space. This idea was once deeply unsettling. How could one body affect another without touching it? Newton himself was uncomfortable with the notion, describing it as action at a distance. Over time, physicists grew accustomed to this kind of influence. Fields were introduced as a way to describe how forces extend through space. Instead of objects reaching out directly, space itself carries information about how objects should move. Gravity, in this view, fills space with a pattern that guides motion. This way of thinking opened the door to understanding other interactions that behave similarly. If gravity can act across emptiness, perhaps it is not alone. Perhaps space is threaded with multiple influences, each following its own rules, each shaping motion in subtle ways. From falling objects to planetary systems, gravity provides a unifying explanation that ties together the small and the vast. It shows that the universe is not a collection of isolated events, but a connected whole, where motion in one place reflects influences from another. And while gravity governs structure and stability, it is only one of several interactions that operate without contact. To fully understand how forces shape the universe, attention must widen to include other invisible influences that move energy, matter, and information across space just as reliably. Gravity shows that space can carry influence without touch. Electricity and magnetism reveal that this idea runs much deeper. Unlike gravity, which depends only on mass, electrical and magnetic effects arise from a property called charge. Charge comes in two varieties: commonly described as positive and negative. Like charges repel, opposite charges attract. This simple rule gives rise to a remarkable range of behavior, from sparks and lightning to the quiet flow of electricity through a wire. Electric charge is everywhere. Atoms are built from charged components. Electrons carry negative charge. Atomic nuclei carry positive charge. Most objects appear neutral only because their charges balance almost perfectly. Disturb that balance slightly, and electrical forces become obvious very quickly. A rubbed balloon clings to a wall. A shock jumps from a doorknob. Hair lifts and separates. These are not dramatic exceptions. They are everyday reminders that electrical forces are constantly present, usually cancelling themselves out so neatly that they go unnoticed. Magnetism seems, at first, like a separate phenomenon. Magnets attract and repel. Compasses align themselves with the Earth. Electric currents cause needles to move. For centuries, electricity and magnetism were studied as distinct curiosities, each with its own rules and oddities. The deeper connection between them emerged slowly, through careful experimentation. In the early 19th century, it became clear that moving electric charges create magnetic effects. A current flowing through a wire produces a magnetic field around it. Change the current, and the magnetic influence changes as well. Later experiments showed the reverse is also true. Changing magnetic environments induce electric currents. Motion through a magnetic field can generate electricity. This principle underlies electric generators, which quietly convert mechanical motion into electrical energy across the world. What these discoveries revealed was not two separate forces, but one unified interaction. James Clerk Maxwell provided the mathematical framework that brought electricity and magnetism together. His work showed that electric and magnetic effects are inseparable aspects of a single phenomenon, now called electromagnetism. Changes in electric fields produce magnetic effects. Changes in magnetic fields produce electric effects. Together they form a self-sustaining system. Maxwell's equations, spoken rather than written, describe how electric fields and magnetic fields influence one another and propagate through space. One of their most profound implications is that disturbances in these fields can travel on their own, without any material medium. These travelling disturbances are electromagnetic waves. Light, it turns out, is one of them. This realization was astonishing. Light had long been studied as something separate with its own optical laws. Maxwell's work revealed that light is not an add-on to physics, but a natural consequence of electromagnetic behavior. When electric and magnetic fields oscillate together, they produce waves that move through space at a fixed speed. Measurements of this speed match the known speed of light precisely. There was no ambiguity. Light was electromagnetism in motion. This insight unified entire branches of science. Optics, electricity, magnetism, and radiation became parts of a single framework. Technologies that followed, from radio communication to modern electronics, rest directly on this understanding. The concept of a field is central here. A field is not a physical object. It is a description of how space behaves in the presence of charge or current. Place a charged object in space, and the surrounding region gains structure. Other charges respond to that structure. Remove the charge and the structure vanishes. The field carries information about how objects should move if they enter it. Fields allow forces to act without direct contact. They replace the unsettling idea of action at a distance with a gentler picture. Space itself participates. It is not empty and passive. It has properties that can change and evolve. This view explains why electromagnetic effects can travel through a vacuum. No wires are needed. No particles must be carried along. The fields themselves ripple outward, transferring energy and information. Everyday life depends on this constantly. Radio signals travel invisibly through space. Mobile phones exchange information through electromagnetic waves. Microwaves warm food by interacting with molecular motion. Medical imaging uses carefully tuned radiation to reveal internal structure without physical intrusion. Scientific institutions around the world rely on electromagnetic theory to design instruments, satellites, and observatories. Telescopes collect light that has travelled for billions of years. Detectors measure faint electromagnetic signals from distant galaxies. All of this works because electromagnetic behaviour is stable, predictable, and well understood. There's also a pleasing symmetry to electromagnetism. Positive and negative charges balance. Electric and magnetic fields intertwine. Motion and change are inseparable. What appears as a static electric field in one frame of reference can appear partly magnetic in another. The distinction depends on perspective. This hints at something deeper. Forces may not be as separate as they appear. What looks like one interaction under certain conditions may reveal another face when motion is involved. Nature seems fond of unity beneath diversity. Electromagnetism also introduces an important new idea. Not all interactions require mass. Light carries energy and momentum without having rest mass. It exerts pressure. It transfers information. It influences matter. This challenges intuition built from mechanics alone. Even gentle sunlight carries momentum. Solar sails proposed for spacecraft rely on this fact, using radiation pressure to provide slow but steady acceleration. Over long periods, even small influences matter. There is gentle humour in realising how much of modern life depends on invisible waves passing effortlessly through walls, air and space, all while remaining completely unnoticed unless something goes wrong. Electromagnetism bridges the gap between forces and radiation. It shows how interactions can propagate, how influence can travel, and how energy can move independently of matter. Fields are not static backdrops. They're active participants in physical processes. Once this is understood, attention naturally shifts again. If electromagnetic fields can carry energy outward as waves, then radiation becomes a central theme. Light is only one example. A broader spectrum of radiation exists, each part governed by the same underlying rules. From here, the universe begins to glow in new ways. Once electricity and magnetism were understood as a single, unified interaction, light took on a new role. It was no longer just something that illuminated objects or revealed colours. It became a physical phenomenon in its own right, a moving pattern of energy, a messenger that carries information across space without needing matter to go along for the ride. Light is electromagnetic radiation. That phrase can sound abstract, but its meaning is gentle. Light is what happens when electric and magnetic fields oscillate together and travel outward through space. These oscillations do not require air, wires, or particles as carriers. They move through empty space just as easily as through glass or water, changing speed slightly depending on the medium, but never needing one. This realization transformed physics. For centuries, light had been treated as something separate. Optics described reflection and refraction. Astronomy tracked starlight across the sky. But when electromagnetic theory revealed that light itself was a wave made of fields, it became clear that illumination was simply one part of a much broader spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays all follow the same rules. They differ only in how rapidly their fields oscillate. What makes light especially remarkable is not just what it is, but how it behaves. No matter who measures it, or how fast the observer is moving, the speed of light in empty space remains the same. This constancy is not an approximation. It has been confirmed repeatedly through careful experiment. Whether measured on Earth, aboard satellites, or inferred from astronomical observations, the value does not change. This was deeply unsettling when first discovered. In everyday life, speeds add and subtract. Walk forward on a moving train and speed increases. Walk backward and it decreases. Light refuses to play along, even if the source is moving rapidly, even if the observer is racing toward it. Light arrives at the same speed it always does. Albert Einstein took this fact seriously. Rather than treating it as an inconvenience to be explained away, Einstein built an entire framework around it. He proposed that the speed of light is not just a property of light, but a fundamental feature of reality itself. Space and time must adjust so that this speed remains constant for all observers. This was not a small change. It meant that measurements of distance and duration could no longer be absolute. Lengths could contract. Clocks could tick at different rates. What seemed fixed in one frame of reference could vary in another. Light, by insisting on its constancy, forced a re-evaluation of space and time themselves. Long before this rethinking took place, light had already been quietly measuring the universe. Astronomy depends entirely on light. Every distant object is known only through the radiation it sends across space. When observing a star 1,000 light-years away, the light arriving now began its journey 1,000 years ago. Looking farther means looking further back in time. Telescopes are not just instruments of distance, they're instruments of history. This scale is difficult to grasp. Light from the Sun takes a little over 8 minutes to reach Earth. Light from the nearest star beyond the Sun takes more than 4 years. Light from distant galaxies has been travelling for billions of years, crossing expanding space, passing through dust and gas, bending around massive objects, yet still arriving with information intact. International observatories and space-based telescopes are designed to capture these faint signals. Each photon carries clues about temperature, motion, composition, and age. By studying slight shifts in wavelength, astronomers can determine how fast an object is moving, whether it's approaching or receding, and even how fast the universe itself is expanding. Light also reveals limits. Because the speed of light is finite, there are regions of the universe from which light has not yet reached Earth. There are also regions from which light never will, not because nothing exists there, but because space itself expands too quickly. Light defines a horizon, not a wall, but a boundary beyond which observation becomes impossible. This makes light more than a messenger. It's a gatekeeper of knowledge. Even close to home, light behaves in ways that challenge intuition. It can act like a wave, spreading and interfering. It can also behave like discrete packets of energy when interacting with matter. This dual nature puzzled scientists for decades, and ultimately contributed to the development of quantum theory. Light does not fit neatly into classical categories. It follows its own rules. Yet despite its strangeness, light remains dependable. It reflects predictably from mirrors. It refracts through lenses. It carries energy that can warm skin, power solar panels, and drive chemical reactions. Plants rely on it to build sugars. Eyes rely on it to form images. Life on Earth is shaped by the steady arrival of sunlight from 93 million miles away. There is a quiet humour in realising how much trust is placed in light. Navigation systems rely on signals travelling at light speed. Communication networks move information through optical fibres as pulses of light. Timekeeping systems synchronize clocks using electromagnetic signals. Modern society runs on the assumption that light will behave tomorrow exactly as it did today. This trust is well earned. Measurements of the speed of light are now so precise that the meter itself is defined in terms of how far light travels in a specific fraction of a second. Distance is anchored to light's behaviour. Space borrows its ruler from radiation. Once light is understood as a physical phenomenon governed by strict laws, its implications deepen. If light's speed is fixed, then space and time cannot be independent. They must adjust together to preserve that speed. Motion, distance, and duration become linked in subtle ways. This realization leads away from forces acting within space and toward the structure of space itself. Light does not merely travel through space and time, it reveals their properties. The behavior of light shows that space can stretch, that time can slow, and that simultaneity is not universal. What appears simultaneous in one frame may not be so in another. Light sets the tempo of reality, and everything else keeps time with it. As light moves outward, carrying energy and information, it quietly reshapes understanding of where events happen and when they occur. The universe is no longer a static stage with a ticking clock in the background. It becomes a dynamic setting where space and time respond to motion and mass. From here, the focus shifts naturally. If light defines limits, sets speeds, and links distance with duration, then space and time themselves must be examined more closely. They are no longer passive containers. They are active participants in the laws that govern reality. Once the behavior of light is taken seriously, space and time can no longer remain quietly in the background. They begin to bend, stretch, and adjust in response. What once seemed like a rigid stage turns out to be flexible, responsive, and deeply intertwined with motion and mass. This is the heart of relativity. At the beginning of the 20th century, Albert Einstein proposed that the laws of physics should look the same to all observers who are moving at constant speeds, and that the speed of light should be identical for everyone, regardless of how they move. These ideas form what is known as special relativity. They sound simple, almost polite, but their consequences are anything but ordinary. If light's speed never changes, then something else must give. Space and time themselves take on that role. Time dilation is one of the first effects to emerge. When an object moves rapidly, time for that object passes more slowly compared to time for something at rest. This is not a trick of perception or a failure of clocks. Time itself unfolds at different rates depending on motion. A clock carried aboard a fast-moving spacecraft will genuinely tick more slowly than one left behind. This effect has been confirmed repeatedly. Atomic clocks placed on aircraft and satellites tick at slightly different rates than clocks on the ground. Global positioning systems must account for this difference to maintain accuracy. Without corrections based on relativity, navigation errors would accumulate rapidly, drifting by kilometers each day. The fact that everyday technology depends on these adjustments is one of the clearest demonstrations that time dilation is real. Length contraction accompanies this slowing of time. Objects moving relative to an observer appear shortened along the direction of motion. Again, this is not a visual illusion. It is a physical effect arising from how space and time reorganize themselves to preserve the constancy of light speed. These changes are subtle at ordinary speeds. Walking, driving, or even flying barely produces noticeable effects. It is only when speeds approach that of light that space-time begins to behave in ways that challenge intuition. This is why relativity remained largely theoretical until technology advanced enough to test it. Special relativity reshaped understanding of motion, but it left gravity unchanged. Gravity still appeared as a force acting across space. Einstein suspected this picture was incomplete. The key insight that led to general relativity came from a simple observation. Being in free fall feels like weightlessness. Astronauts orbiting Earth experience this constantly. They are falling around the planet, not floating away from it. In that state, gravity seems to vanish. Einstein realized that gravity might not be a force in the traditional sense at all. Instead, it could be a consequence of how mass and energy shape space-time itself. In general relativity, space and time are fused into a single entity called space-time. Massive objects do not pull on one another through invisible threads. Instead, they curve the space-time around them. Other objects move along paths shaped by that curvature. What feels like a force is actually motion following the geometry of space-time. A familiar analogy helps here. Imagine rolling a ball across a stretched surface. If the surface is flat, the ball moves straight. If the surface is curved by a heavy object placed at its center, the ball's path bends. The ball is not being pulled sideways by an unseen force. It is following the shape beneath it. In this view, planets orbit stars because space-time is curved by mass. Light bends when passing near massive objects because space-time itself is curved, not because light has weight. Even time flows differently near massive bodies, slowing slightly in stronger gravitational fields. This has been confirmed through observation. Clocks closer to Earth's surface tick more slowly than clocks farther away. Satellite systems must account for this gravitational time dilation, alongside the effects of motion. Precision experiments have measured these differences directly, finding exact agreement with predictions. Astronomical observations provide further support. Light from distant stars bends as it passes near massive galaxies, producing distortions known as gravitational lensing. Entire galaxy clusters can magnify and warp background light, revealing mass distributions that would otherwise remain hidden. These effects match general relativity with remarkable accuracy. One of the most striking confirmations came from the observation of gravitational waves. These are ripples in space-time itself, produced by accelerating massive objects such as merging black holes. Detectors on Earth have measured these faint disturbances, arriving exactly as predicted by Einstein's equations spoken aloud as space-time curvature responds to energy and momentum. General relativity replaces gravity as a force with gravity as geometry. This shift explains why gravity is so universal, and why it cannot be blocked. Objects do not exchange gravitational particles in the same way electric charges exchange photons. Instead, everything moves within the same curved space-time. There is no escaping geometry. Despite its elegance, relativity does not overthrow earlier laws. In gentle conditions, where speeds are low and gravitational fields are weak, classical mechanics works beautifully. Newton's equations emerge as excellent approximations. Bridges still stand. Planets still orbit predictably. Engineers can safely ignore space-time curvature when building roads. Relativity matters when extremes are involved. High speeds, strong gravity, precise timing. In those regimes, space-time reveals its flexibility. There's also a quiet humility in this progression. Each new framework does not declare the old one wrong. It shows where it applies and where it needs refinement. Motion laws describe behavior well at human scales. Relativity extends that understanding into regimes previously unreachable. And yet, relativity itself has limits. At very small scales, space-time becomes jittery. Quantum effects dominate. The smooth curves of general relativity give way to uncertainty and fluctuation. Attempts to merge quantum mechanics with space-time geometry remain incomplete. The laws that describe the very large and the very small do not yet fit together seamlessly. This does not diminish the success of relativity. It highlights how layered physical law truly is. Different descriptions apply in different domains, each accurate within its own territory. Relativity teaches that space and time are not passive containers. They are dynamic participants in the universe's behavior. They stretch with expansion, slow near mass, and respond to energy in measurable ways. Motion is no longer just something that happens within space-time. Motion reshapes space-time itself. There is gentle humour in realising that even the steady ticking of a clock depends on where it is and how it moves. Time, once thought absolute and universal, turns out to be negotiable. As understanding deepens, attention turns again toward boundaries. Classical laws work well, but they falter at extremes. Relativity explains much, but not everything. At the smallest scales, new rules begin to assert themselves, and familiar ideas of position, trajectory, and certainty start to blur. Where space-time bends smoothly, another layer of law waits beneath, ready to take over when classical descriptions can no longer hold. By the early 20th century, physics appeared almost complete. Motion was understood, energy was conserved, time and space had revealed their flexibility, gravity had become geometry. The universe, it seemed, was governed by elegant laws that worked everywhere they were tested. And then, quietly, those laws began to fail, not dramatically, not all at once, but in specific situations, at very small scales. Careful experiments produced results that refused to cooperate. Measurements no longer matched predictions. Patterns that worked beautifully for planets and pendulums began to unravel when applied to atoms and light. This was not a crisis of imagination. It was a crisis of precision. Classical physics assumes that objects have definite positions and velocities at all times, that trajectories can be traced smoothly, that causes produce effects in continuous ways. These assumptions work extremely well for everyday experience. They remain indispensable for engineering, astronomy, and most practical applications. But nature, when examined closely enough, turns out to be less accommodating. Consider light. Classical electromagnetism describes light as a wave spreading smoothly through space. That picture explains reflection, refraction, and interference perfectly. Yet when light interacts with matter at very small scales, the wave description breaks down. Experiments showed that light deposits energy in discrete packets rather than continuous streams. This became impossible to ignore in studies of heated objects. When materials were warmed, classical theory predicted they should emit infinite energy at high frequencies. This clearly did not happen. Measurements showed a sharp cutoff. Something was limiting how energy could be exchanged. Max Planck proposed a solution that was intended as a mathematical convenience, rather than a revolution. He suggested that energy could only be emitted or absorbed in discrete amounts, proportional to frequency. Energy, at small scales, behaved as if it came in steps. The fix worked. The predictions matched observations exactly, but it came at a cost. The idea of continuous energy flow had to be abandoned, at least in certain contexts. Energy, once thought smooth and divisible without limit, appeared granular. Similar surprises followed. Electrons orbiting atomic nuclei did not radiate energy continuously and spiral inward, as classical physics predicted. Instead, atoms were stable. They occupied specific energy states and transitioned between them abruptly. Spectral lines appeared where smooth bands were expected. Matter behaved as if only certain arrangements were allowed. Even the act of measurement began to misbehave. Attempts to pinpoint both the position and motion of particles ran into unavoidable limitations. The more precisely one quantity was determined, the less certain the other became. This was not due to faulty instruments. It was a property of nature itself. Classical intuition began to wobble. At these scales, particles did not behave like tiny billiard balls. They did not follow precise paths. They did not always occupy a single location. Instead, they exhibited wave-like behavior, spreading out, interfering with themselves, and producing outcomes that could only be described probabilistically. This did not mean that physics had failed. It meant that its domain of validity had boundaries. The breakdown of classical physics did not arrive as a declaration that everything was wrong. It arrived as a realization that something new was needed to describe a different layer of reality. The old laws still worked where they had always worked. Bridges did not collapse. Planets did not drift off course. Motion at human scales remained predictable. What failed was the assumption that the same description could be applied without modification everywhere. This distinction is important. Physics progresses not by replacing truths, but by refining their scope. Classical mechanics remains an excellent approximation for large systems. Relativity extends that approximation to high speeds and strong gravity. At small scales, another framework takes over. That framework became known as quantum theory. Quantum theory did not discard classical ideas out of spite. It preserved them where they belonged. In fact, one of its central requirements is that it must reproduce classical behavior in the appropriate limits. When systems become large, or when interactions involve many particles, quantum effects average out, and classical laws reappear naturally. This continuity is one of the most reassuring features of physics. New theories do not invalidate experience. They explain why experience works the way it does. Still, the transition is unsettling. Quantum theory replaces certainty with probability. It describes what is likely to happen rather than what must happen. It predicts distributions of outcomes rather than single trajectories. This feels unfamiliar not because it is chaotic, but because it operates at a level where individual events are not directly observable. At these scales, asking where something is becomes less meaningful than asking how likely it is to be found somewhere. Motion is no longer a line drawn through space, but a spread of possibilities that evolves over time. There is gentle humour in the fact that the universe appears calm and deterministic at large scales, only to reveal a shimmering uncertainty underneath. Like a smooth ocean surface hiding countless ripples, classical behaviour emerges from underlying complexity. Scientific institutions around the world grappled with these ideas throughout the early 20th century. Experiments became more refined. Predictions became more precise. Quantum theory passed test after test, often with astonishing accuracy. Measurements of atomic transitions, particle behaviour and radiation matched theory to many decimal places. And yet the theory resisted comfortable interpretation. What does it mean for a particle to be in multiple places at once? What determines the outcome of a measurement? Is probability fundamental, or a reflection of incomplete knowledge? These questions lingered and still do, without threatening the practical success of the theory itself. The important point here is not philosophical discomfort, but explanatory power. Quantum theory explains why atoms are stable. It explains why matter has structure. It explains chemical bonding, electrical conductivity, and the behavior of semiconductors. Modern electronics, lasers, and medical imaging depend directly on quantum principles. Without them, much of contemporary technology would simply not exist. The breakdown of classical physics, then, was not a collapse. It was a doorway. It showed that reality is layered. Different descriptions apply at different scales. The laws that govern planets are not wrong, but incomplete when applied to electrons. The universe does not contradict itself. It reveals itself gradually, changing language as the scale changes. There is also a quiet lesson in humility here. Each time physics has seemed nearly finished, nature has produced a new detail that demanded attention. Precision exposed surprise. Certainty gave way to deeper structure. This pattern suggests that laws are not declarations etched into the universe, but models refined through encounter. They work because they match observation, not because they are final. As attention moves fully into the small-scale world, familiar ideas continue to soften. Position becomes fuzzy, energy becomes quantized, outcomes become statistical. Yet underlying these shifts is remarkable order. Quantum theory is not lawless. It is governed by strict rules, just different ones. To To understand how these rules operate and how they reshape the concept of reality itself, the focus must now turn fully toward the quantum domain. When classical ideas finally loosen their grip, matter begins to behave in unfamiliar but surprisingly disciplined ways. The quantum world does not abandon rules. It replaces smoothness with steps, certainty with structure, and continuity with carefully measured change. One of the first signs of this shift is quantization. In everyday experience, energy seems endlessly divisible. A light can be dimmed gradually. A sound can fade smoothly. Motion can slow by any amount. Classical physics assume this continuity applied everywhere. At small scales, experiments showed otherwise. Energy, when exchanged between matter and radiation, arrives in discrete portions. It does not trickle, it transfers in packets. These packets are not arbitrary. Their size depends on the frequency of the radiation involved. Higher frequency means larger energy steps. Lower frequency means smaller ones. This idea first appeared in the work of Max Planck at the turn of the 20th century. While studying how heated objects emit light, Planck found that classical theory predicted infinite energy at high frequencies, something clearly contradicted by experiment. To fix the mismatch, he proposed that energy exchange was quantized. At the time, this was meant as a mathematical solution, not a philosophical statement. But the fix worked too well to ignore. The data matched perfectly. Quantization soon appeared elsewhere. Atoms absorbed and emitted light only at specific frequencies. Their energy levels were not continuous bands, but sharply defined steps. Electrons did not spiral freely around nuclei. They occupied distinct states. Transitions between those states produced precise spectral lines that could be measured with extraordinary accuracy. These observations were not subtle. Laboratories across the world reproduced them again and again. The quantum behavior of matter was not a theoretical curiosity. It was experimentally undeniable. Alongside quantization came another unsettling feature. Objects traditionally thought of as particles began to show wave-like behavior. Electrons produced interference patterns. Neutrons diffracted. Even large molecules exhibited wave properties under carefully controlled conditions. At the same time, light, long described as a wave, displayed particle-like behavior. It transferred energy in discrete amounts. It produced localized impacts on detectors. It behaved as if it arrived in individual quanta rather than continuous ripples. This dual behavior is known as wave-particle duality. It does not mean that objects switch identities depending on mood. It means that neither the classical idea of a particle nor that of a wave is sufficient on its own. Quantum entities follow rules that include aspects of both. The key is context. When interacting with measuring devices, quantum systems produce localized outcomes. A detector registers a click. A screen shows a point of impact. When allowed to evolve freely, those same systems spread out, interfere with themselves, and behave like waves. Both descriptions are accurate but incomplete in isolation. This is not philosophical hand-waving. It is grounded in experiment. The famous double-slit experiment demonstrates this vividly. When particles such as electrons pass through two narrow openings one at a time, they produce an interference pattern over time. Each particle arrives at a single point, yet the overall distribution reveals wave behavior. If the setup is altered to determine which slit the particle passes through, the interference disappears. The act of measurement changes the outcome. Quantum theory accounts for this precisely. It predicts probabilities rather than paths. It does not say where a particle is, but where it is likely to be found. The probabilities evolve smoothly according to strict mathematical rules, Even though individual outcomes appear random, there's a gentle humour in realising that nature, at its smallest scales, behaves more like a careful statistician than a clockwork machine. Despite this probabilistic character, quantum theory is one of the most accurate frameworks ever developed. Predictions match experiments to extraordinary precision. Measurements of atomic transitions agree with theory to many decimal places. Semiconductor behavior, laser operation, and chemical bonding all follow quantum rules with remarkable reliability. This success is not accidental. Quantum theory was built not from speculation but from data. Each strange feature emerged because experiments demanded it. Whenever theory resisted, measurement prevailed. Large scientific institutions continue to test quantum predictions relentlessly. Particle accelerators probe interactions at tiny scales. Spectroscopic studies examine energy levels with exquisite resolution. Every test reinforces the same conclusion. Matter behaves quantum mechanically. What often causes confusion is the scale gap between quantum behavior and everyday experience. The quantum world feels unfamiliar because its effects average out when many particles are involved. A grain of sand contains more atoms than can easily be imagined. Their individual uncertainties cancel, producing stable, classical behavior. This is why chairs remain solid and walls do not flicker. Quantum rules do not vanish at large scales. They become hidden beneath collective behavior. Another important point is continuity. Quantum theory does not erase classical physics. It explains why classical physics works where it does. When energies are high, distance is large, and systems complex, quantum probabilities cluster tightly around classical predictions. Classical motion emerges as an approximation, not a contradiction. This layered structure is one of physics' great strengths. Different laws apply at different scales, yet they fit together without conflict. Each framework respects the others within appropriate limits. Quantization also explains stability. Without it, atoms would collapse. Matter would not hold shape. Chemistry would be impossible. The existence of solid objects depends on the fact that energy levels are discrete and constrained. There is something quietly reassuring about this. The solidity of the world, the reliability of materials, and the structure of matter all arise from quantum rules that never announce themselves directly. Still, one feature remains unresolved. Quantum theory describes probabilities with precision, but it places limits on what can be known simultaneously. Some quantities cannot be pinned down at the same time, no matter how carefully measurements are made. This is not due to technological weakness. It is woven into the framework itself. As attention moves deeper into the quantum domain, the focus shifts from what happens to what can be known, from outcomes to limits, from motion and energy to uncertainty itself. Understanding those limits reveals not chaos, but another layer of order. As quantum behavior becomes familiar, a new kind of limit quietly takes shape. Not a technical limitation that better instruments might overcome, but a fundamental boundary built into the structure of nature itself. This boundary does not forbid knowledge entirely. It defines how knowledge must be shared. This idea is known as the uncertainty principle. At first encounter, it is often misunderstood. It is sometimes described as a statement about experimental clumsiness, or about observers disturbing what they measure. While measurement does play a role, the deeper meaning runs further. The uncertainty principle is not about human error. It is about how certain properties of the universe are related. Werner Heisenberg, working in the early 20th century, noticed that some quantities refuse to be sharply defined at the same time. The most familiar pair is position and motion. The more precisely a particle's position is specified, the less precisely its motion can be known, and the more accurately its motion is pinned down, the more its position spreads out. This is not a statement about inconvenience. It is a statement about structure. In classical physics, position and motion are independent. A ball can have an exact location and an exact speed simultaneously. Quantum theory does not allow this pairing to be infinitely precise. The two descriptions draw from the same underlying information, and sharpening one inevitably blurs the other. This relationship can be summarized by an equation often written symbolically, but spoken aloud it becomes the uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to a small constant divided by 2. The exact form matters less than the message. There is a lower bound, a trade-off that cannot be negotiated away. What makes this surprising is that it applies even in perfect conditions, even with ideal instruments, even in complete isolation. The uncertainty does not come from noise or disturbance. It comes from the wave-like nature of matter itself. A quantum particle is not a point moving along a track. It is described by a spread-out pattern. This pattern encodes probabilities. It evolves smoothly over time, but it does not collapse into a single path until interaction occurs. Asking for both exact position and exact motion is like asking a melody to be both a single note and a full chord at the same time. The uncertainty principle does not imply chaos. The probabilities involved are precise. Quantum theory predicts distributions with extraordinary accuracy. What is lost is not predictability, but determinism at the level of individual events. The theory tells what will happen on average and how likely different outcomes are, not which specific one will occur in advance. This distinction is subtle but crucial. A radioactive atom does not decay randomly in the sense of lawlessness. Its behavior follows strict statistical rules. Over large numbers, decay rates are perfectly predictable. What cannot be predicted is the exact moment a single atom will decay. The uncertainty is not ignorance. It is irreducible. This replacement of certainty with probability marks a shift in how explanation works. In classical physics, knowing the present in sufficient detail allows the future to be calculated exactly. In quantum physics, knowing the present allows the future to be described probabilistically. The future is constrained, structured and lawful, but not fixed in detail. There is gentle humour in the fact that this deeply unsettling idea produces some of the most reliable predictions ever made. Quantum calculations underpin technologies that function flawlessly day after day. Lasers emit light with exquisite precision. Atomic clocks keep time so accurately that relativistic effects must be accounted for. Semiconductors behave exactly as probability predicts. The uncertainty principle also places limits on observation itself. To measure position, interaction is required. To detect a particle, energy must be exchanged. That interaction changes the system. But even without considering disturbance, the quantum description already limits what can be simultaneously specified. The universe does not contain hidden precise values waiting to be uncovered. Some values are simply undefined until measured. This does not mean reality is incomplete. It means it is different from classical expectation. Importantly, uncertainty does not apply to everything equally. Large objects composed of many particles exhibit negligible quantum uncertainty in position and motion. The uncertainties average out. Classical certainty emerges naturally. This is why the world appears stable and well-defined at everyday scales. Quantum uncertainty becomes dominant only when dealing with individual particles or tightly confined systems. In those regimes, it is not a nuisance. It is essential. Without uncertainty, atoms would collapse, electrons would spiral into nuclei, matter would not exist in recognizable form. Uncertainty provides structure. It sets the scale of atomic orbitals. It determines the size of atoms. It governs the pressure that keeps white dwarf stars from collapsing. It is responsible for effects that prevent matter from becoming infinitely dense under ordinary conditions. Scientific institutions have tested these implications extensively. Spectroscopy reveals energy levels exactly where uncertainty predicts they should be. Particle beams spread in ways that match probabilistic forecasts. No experiment has ever found a violation. There's also a philosophical temptation to treat uncertainty as a statement about knowledge rather than nature. This temptation is understandable, but misleading. The uncertainty principle is not saying that something exists but cannot be known. It is saying that the thing itself does not exist in the classical sense until interaction defines it. Position and motion are not properties carried around independently by particles. They are contextual features that emerge through interaction. The universe is not hiding information. It is offering information in a different format. This has consequences for how explanation proceeds. Instead of tracking trajectories, physics tracks amplitudes. Instead of certainties, it tracks likelihoods. Instead of asking what is happening, it asks what can happen and how often. This shift does not weaken explanation, it deepens it. Probability in quantum theory is not an admission of defeat, it is a complete description. Given a quantum state, all possible outcomes and their likelihoods are specified exactly. Nothing is missing. There is a quiet elegance here. Nature does not roll dice arbitrarily. It follows probability distributions with unwavering consistency. The randomness lies not in the rules, but in the outcomes. As understanding settles into this probabilistic framework, attention moves again. Quantum theory describes uncertainty, but it also describes entities that carry specific properties: charge, mass, spin. These are not fuzzy in the same way. They are sharply defined. To understand how the universe is built from such entities, and how they interact under quantum rules, the focus turns from uncertainty itself to the particles that embody it. Once uncertainty is accepted as a feature rather than a flaw, the quantum world begins to look less mysterious and more structured. Beneath the probabilities and wave-like behavior lies a surprisingly orderly cast of characters. Matter is not continuous. It is assembled from distinct ingredients, each following well-defined rules. These ingredients are particles. Particles come in families, not as a matter of convenience, but because experiments insist on it. Some particles make up matter itself. Others carry forces between them. Some are stable. Others exist only fleetingly before transforming into something else. Together they form the basic inventory from which everything familiar is built. The particles that make up matter are known as fermions. Among them are quarks and leptons. Quarks combine to form protons and neutrons, which in turn form atomic nuclei. Leptons include electrons, which orbit those nuclei, as well as neutrinos, which pass through almost everything without leaving much trace. These particles are not interchangeable. Each has specific properties. Mass, electric charge, and an intrinsic form of angular momentum called spin are fixed characteristics. An electron is always an electron. A quark of a given type never gradually becomes another kind. Identity is preserved. Quarks themselves come in different varieties, often referred to as flavors. They never appear alone under ordinary conditions. Instead, they bind together through a powerful interaction known as the strong force. This force is responsible for holding atomic nuclei together, overcoming the natural electrical repulsion between positively charged protons. The strong force is remarkably intense, but its reach is short. It operates only at very small distances, comparable to the size of atomic nuclei. Within that range, it dominates all other interactions. Beyond it, it fades rapidly, leaving larger structures to be governed by other rules. Electrons and other leptons interact primarily through the electromagnetic force. This force governs attraction and repulsion between charges, binds electrons to nuclei, and underlies chemistry. It is long-ranged, acting across vast distances, but weaker than the strong force at close quarters. There is also a third interaction relevant at the particle scale, the weak force. Despite its name, it plays a crucial role in processes that change one type of particle into another. It governs radioactive decay and enables nuclear reactions that power stars. Without the weak force, the sun would not shine. Together, the strong force, the electromagnetic force, and the weak force govern nearly all particle interactions observed in laboratories and throughout the universe. Gravity, while fundamental at large scales, is so feeble at the particle level that it can usually be ignored in these contexts. These interactions are mediated by particles of their own. Photons carry electromagnetic influence, gluons carry the strong force, other particles carry the weak interaction. When particles interact, they exchange these carriers. Forces become conversations rather than pulls. Momentum, energy, and other quantities are traded through these exchanges according to strict rules. The framework that organizes this entire picture is known as the Standard Model of particle physics. The Standard Model is not a single equation or diagram. It is a comprehensive description of particle types and their interactions, built from decades of experimental evidence. It classifies particles into families, specifies how they interact, and predicts outcomes with extraordinary accuracy. What makes the Standard Model remarkable is not just its scope, but its precision. Predictions derived from it have been confirmed to many decimal places. Experiments measuring particle behavior consistently match theoretical expectations. Few scientific theories have ever been tested so rigorously. Large research institutions play a central role in this work. Particle accelerators propel particles to enormous energies and bring them into controlled collisions. Detectors surrounding these collision points record the debris, allowing physicists to reconstruct what occurred. One of the most prominent of these facilities is the European Laboratory for Particle Physics, where accelerators stretch for many kilometers underground. There, particles are guided along circular paths, accelerated to near light speed, and made to collide head-on. The resulting interactions briefly recreate conditions similar to those that existed shortly after the universe began. These experiments are not acts of destruction, but of inquiry. By breaking particles apart, their internal structure and governing rules are revealed. New particles can appear momentarily, leaving signatures that confirm theoretical predictions or hint at something unexpected. This approach led to the discovery of particles that complete the Standard Model, including those responsible for giving mass to others. Each discovery was less a surprise than a confirmation, a missing piece clicking into place. There is gentle humour in the fact that some of the universe's most fundamental truths require machines the size of cities to uncover, all to observe events that last less than a trillionth of a second. Despite its success, the Standard Model is not considered final. It does not include gravity. It does not explain why particles have the masses they do. It does not account for dark matter, which appears to influence galaxies but does not interact electromagnetically. These gaps are well known and actively studied. Still, within its domain, the Standard Model works astonishingly well. It explains why matter is stable. It explains why chemical elements behave the way they do. It explains why radioactive decay follows predictable patterns. It explains why particles can transform while preserving certain quantities exactly. Those preserved quantities hint at something deeper. In every interaction, certain properties remain unchanged. Electric charge is conserved. Energy and momentum are conserved. Other quantities, less familiar but equally important, are preserved as well. These conservation laws are not arbitrary. They reflect hidden regularities in the structure of physical law. Physicists notice that whenever a conservation law exists, it corresponds to a kind of symmetry, a sameness under change. Rotate a system and its behavior remains the same. Shift it in time and the laws still apply. Exchange one particle for another in a specific way, and the interaction remains allowed. This connection between symmetry and conservation is not a coincidence. It is one of the deepest insights in modern physics. The laws governing particles are not just lists of ingredients and interactions. They are expressions of symmetry. They reveal that nature cares less about specific arrangements and more about patterns that remain unchanged under transformation. As understanding deepens, the focus moves away from particles themselves and toward these underlying symmetries, the rules that dictate what can happen, what must happen, and what can never happen. In that sense, particles are not the final story. They are the visible manifestations of something more abstract, a quiet order that shapes interactions without announcing itself. To uncover that order, attention must shift from what particles are to why their behavior is so constrained, and why certain patterns repeat no matter how the pieces are rearranged. As the catalogue of particles and forces grows more complete, a quieter pattern begins to stand out. Beneath the details of mass and charge, beneath the complexity of interactions and transformations, something remarkably simple keeps appearing. Certain features of the universe refuse to change, even as everything else does. This idea is called symmetry. In everyday language, symmetry often means visual balance, a face that mirrors itself, a shape that looks the same when rotated. In physics, symmetry means something more general and more powerful. It means invariance under change. A system may shift, rotate, evolve, or transform, yet some aspect of it remains exactly the same. This sameness is not decorative, it is structural. Imagine performing an experiment today or tomorrow. The outcome does not depend on the date. Perform it here or a few meters away, and the same laws apply. Rotate the entire setup, and nothing fundamental changes. These are examples of symmetry. The universe does not care when or where an experiment is performed, or which direction it faces. These quiet indifferences have consequences. Whenever a system exhibits a symmetry, something is conserved, not by coincidence, but by necessity. This connection is so reliable that it has become one of the guiding principles of modern physics. Consider time. The laws of physics do not change from one moment to the next. This symmetry in time leads directly to the conservation of energy. Energy remains constant because the rules governing processes are the same today as they were yesterday. Consider space. The laws of physics do not depend on location. This symmetry in position leads to the conservation of momentum. Motion continues unless acted upon because shifting a system through space does not alter the underlying rules. Consider rotation. The laws of physics are the same in every direction. This symmetry leads to the conservation of angular momentum. Spinning objects continue to spin, and changing their rotation requires interaction. These are not separate observations stitched together after the fact. They are deeply linked. The universe conserves quantities because it is symmetric in specific ways. This relationship was formalized in the early 20th century by Emmy Noether, whose work revealed the precise connection between symmetry and conservation. Noether showed that for every continuous symmetry in a physical system, there exists a corresponding conserved quantity. Her insight did not add a new law to physics. It explained why laws look the way they do. Energy conservation is not a standalone rule. It arises because the universe does not favor one moment over another. Momentum conservation exists because space does not privilege one location. Charge conservation reflects a symmetry in how charged particles can be transformed without changing the physics. These ideas may sound abstract, but their effects are constant and concrete. Every collision obeys conservation of momentum. Every engine obeys conservation of energy. Every electrical interaction preserves charge exactly. No experiment has ever observed a violation. When something seems to be missing, it turns out to be hiding in an unexpected form or location. There is a quiet satisfaction in this. Nature does not need to remember rules case by case. Symmetry does the bookkeeping automatically. Even more striking is how these symmetries persist across wildly different scales. The same conservation of momentum governs a drifting spacecraft and a colliding pair of particles. The same energy conservation applies to chemical reactions, nuclear processes, and stellar fusion. The scale changes, the language changes, the symmetry remains. This is why symmetry is often seen as more fundamental than the laws it produces. Laws describe behavior. Symmetry explains why that behavior is constrained in the first place. In particle physics, symmetry plays an even more central role. Particles are not just objects with properties. They are manifestations of underlying symmetries. The types of interactions allowed, the ways particles can transform, and the quantities that must be conserved all follow from symmetry requirements. For example, electric charge is conserved because the equations governing electromagnetic interactions are symmetric under a specific transformation of the electric field. The strong interaction preserves certain quantities because of deeper internal symmetries that organize quarks into families. These symmetries are not visible in everyday space, but they operate in abstract mathematical spaces that shape particle behavior. This may sound remote, but its effects are everywhere. The stability of matter depends on these symmetries. Atoms do not suddenly decay into unrelated fragments because certain transformations are forbidden. Chemical reactions follow predictable patterns because charge and energy must balance exactly. Nuclear reactions release specific amounts of energy because conservation laws leave no room for improvisation. There's also gentle humour in realising how much freedom the universe has and how carefully it restricts itself anyway. Particles may behave probabilistically, but they never cheat on conservation. Randomness operates within firm boundaries. Symmetry also explains why laws are universal. If the same symmetries apply everywhere, then the same laws must apply everywhere. A particle behaves the same on Earth as it does in a distant galaxy, because the underlying symmetries of space and time are the same. This universality allows physics to scale up confidently. Observations made in laboratories can be applied to stars. Experiments conducted with particles can inform cosmology. The same conservation principles that govern a spinning top help explain the rotation of galaxies. As physics progressed, researchers began to notice that many apparently different forces could be described using similar symmetry principles. Electricity and magnetism unified through shared symmetry. The weak interaction joined them through deeper mathematical structure. Patterns began to emerge suggesting that forces might be different expressions of a single underlying framework. Symmetry in this context becomes a guide. Instead of asking which forces exist, physicists ask which symmetries are present. Forces emerge as consequences of requiring those symmetries to hold locally. The interactions are not added by hand. They are demanded by consistency. This approach has proven extraordinarily successful. Entire theories can be constructed by specifying symmetries and letting the mathematics dictate what must follow. When predictions emerge, experiments test them. When they succeed, confidence grows that the symmetry-based approach is capturing something real. At the same time, symmetry is not always perfect. Some symmetries appear broken. Certain processes favour matter over antimatter. Some interactions distinguish left from right. These asymmetries are not failures, they are clues. Broken symmetry often reveals hidden structure, much like a cracked crystal reveals its internal pattern. Physicists pay close attention to these imperfections. They often point toward deeper layers of law. Understanding why a symmetry is broken can be as informative as knowing that it exists. The growing role of symmetry has shifted how laws are viewed. Instead of being treated as separate rules collected from observation, laws are increasingly seen as consequences of deeper principles. The surface behavior flows from underlying invariances. This perspective brings a sense of order to the apparent complexity of nature. Countless interactions, particles, and processes are all constrained by a relatively small set of symmetry requirements. The universe appears diverse, but it is governed by repetition at a deeper level. As this understanding matures, a natural ambition arises. If symmetry explains so much, perhaps all interactions share a common origin. Perhaps the various forces are fragments of a single structure, split apart under different conditions. This idea has motivated decades of research. Efforts to unify forces to describe them within a single framework are driven by the belief that symmetry does not stop where current theories do. The laws already known suggest unity. The question is how far that unity extends. To explore that, physics begins to look beyond individual forces and conservation laws toward the possibility that they are all expressions of one deeper principle, a framework in which the distinctions between interactions dissolve, leaving only structure. Whether such unification exists remains an open question, but the path toward it has been guided again and again by symmetry. As symmetry reveals deeper structure beneath individual laws, a quiet ambition emerges. If so many forces share common patterns, perhaps they are not truly separate at all. Perhaps they're different expressions of a single underlying framework, revealed only under different conditions. This idea has guided physics for more than a century. The first great success came when electricity and magnetism were unified. What once appeared as two distinct forces turned out to be aspects of the same interaction. This was not achieved by clever naming, but by showing that a single set of rules could account for both phenomena simultaneously. Light emerged naturally from that unification, not as an added feature, but as an unavoidable consequence. That success left a lasting impression. If two forces could become one, why stop there? In the 20th century, further progress followed. The weak interaction, responsible for certain forms of radioactive decay, was shown to be closely related to electromagnetism. At high energies, these two forces behave as different faces of a single electro-weak interaction. Only as the universe cooled did they separate into distinct behaviors. This unification was not speculative. It made precise predictions that were later confirmed experimentally. Particles required by the theory were observed. Interaction strengths matched expectation. The framework held together under scrutiny. Encouraged by this, physicists began to ask whether the strong force might also fit into a unified picture. Mathematical models suggested that at extremely high energies, all three non-gravitational forces could converge into a single interaction. These ideas, often grouped under the term grand unification, remain incomplete but intriguing. Some aspects align well with observation, others remain untested. No decisive experimental confirmation has yet been found. The energies required to probe these regimes far exceed what current accelerators can reach. Gravity remains the most stubborn holdout. Unlike the other forces, gravity is described not as an interaction between particles, but as the geometry of space-time itself. Its mathematical language is fundamentally different. Attempts to reconcile gravity with quantum theory have proven extraordinarily difficult. The smooth curves of space-time resist quantization in the same way that energy and matter yield to it. Various approaches have been explored. Some treat gravity as emerging from quantum interactions. Others attempt to quantize space-time directly. Each approach has produced insights, but none has yet delivered a complete testable theory that unites gravity with the other forces under experimental confirmation. This situation is not a failure, it is a boundary. Modern physics is unusually clear about where its understanding ends. The known laws work extraordinarily well within their domains. Predictions are precise, technologies function, observations align, but the edges remain uncertain, and those uncertainties are openly acknowledged. There is humility in this stance. Rather than forcing premature conclusions, physicists treat unification as a guiding question, rather than a finished answer. Mathematical consistency, experimental constraint, and conceptual clarity are all required. No single ingredient is sufficient on its own. Institutions across the world contribute to this effort in complementary ways. Particle accelerators search for deviations from known behavior. Observatories look for subtle gravitational effects. Precision experiments test symmetries to extraordinary accuracy. Each negative result is not disappointment, but information. There is also restraint in how speculative ideas are treated. Proposals that cannot yet be tested are explored cautiously. They are developed mathematically, examined for internal consistency, and compared against known results. But they are not promoted to the status of established law. The distinction between what is known and what is hoped for is carefully maintained. This discipline is one of science's quiet strengths. It allows imagination without surrendering rigor. It permits bold ideas while insisting on evidence. It keeps the boundary between explanation and speculation visible. At the same time, unification remains a powerful organizing principle. Even without final answers, it shapes how questions are asked. It encourages physicists to look for shared structures rather than isolated rules. It suggests that simplicity may lie beneath apparent complexity. There is gentle humor in the fact that every time physics seems close to completion, the universe reveals another layer. Each unification raises new questions. Each success exposes a deeper challenge. This pattern has repeated throughout history. Classical mechanics gave way to relativity and quantum theory. Electromagnetism expanded into electroweak theory. Each step clarified some mysteries while uncovering others. What remains consistent is the method: careful observation, precise measurement, mathematical structure guided by symmetry, willingness to revise assumptions, acceptance of limits. Modern physics does not claim to possess the final description of reality. It claims something quieter, that within its current reach, the universe behaves consistently, and that those consistencies can be described with remarkable accuracy. Unification, in this light, is less about arriving at a single equation, and more about understanding relationships, how different behaviors connect, why certain patterns repeat, where boundaries between laws arise, and why they exist. This perspective shifts emphasis away from final answers and toward interpretation. What does it mean that different laws apply at different scales? Why does nature permit such layered description? Are laws discovered or constructed? Are they properties of the universe, or summaries of how the universe behaves under specific conditions? These questions do not demand immediate resolution, they invite reflection. As the search for unification continues, it becomes clear that understanding the laws of physics is not only about what they say, but about how they are used, how they are framed, how they relate to observation and explanation. At this stage, attention turns inward, away from the ambition to unite everything under one banner, and toward the question of what laws really represent, whether they are commands, descriptions, or something more subtle. That shift does not weaken physics, it deepens it. After centuries of discovery, refinement, and revision, a quieter question remains. When physics speaks of laws, what exactly is being described? It is tempting to imagine laws of physics as rules imposed on the universe, written somewhere beneath reality and enforced without exception. This picture is comforting. It suggests certainty, authority, and finality. But it is not how physics actually works. Physical laws are not commands. They are models. A law of physics is a carefully tested description of how the universe behaves under specific conditions. It is a summary of patterns observed repeatedly, expressed in a form that allows prediction. Nothing more and nothing less. When a law succeeds, it does not mean reality is obeying it. It means the description matches what reality is doing. This distinction matters. Throughout history, laws once thought complete have been refined, extended, or limited. Newton's laws did not vanish when relativity arrived. They remained accurate within a certain range. Classical thermodynamics did not fail when quantum theory appeared. It was shown to emerge naturally when many particles are involved. Each new framework preserved what worked and clarified where it applied. This layered structure reveals something important about scientific knowledge. Laws are not ultimate truths carved into the universe. They are tools. They capture regularities within a domain, and they remain useful as long as observations stay within that domain. Experiment is the quiet judge in this process. A proposed law must survive comparison with measurement. If predictions match results, confidence grows. If discrepancies appear, the law is questioned. Sometimes adjustments are minor, sometimes entirely new ideas are required. In every case, reality has the final say. Large scientific institutions exist largely to carry out this conversation between theory and experiment. Particle accelerators test predictions at small scales. Space missions check gravitational models across vast distances. Precision measurements probe tiny deviations that might signal new physics. The laws survive not because they are elegant, but because they work. This emphasis on prediction often surprises those encountering physics for the first time. Physics is less concerned with why the universe behaves as it does than with how it behaves. A law that predicts accurately is valued even if its deeper explanation remains unclear. Explanation is welcome, but reliability comes first. Knowing what will happen matters more than knowing why it happens. There is a quiet practicality in this approach. When engineers design a bridge, they rely on laws that predict stress and strain. They do not need to know why matter resists deformation at a fundamental level. When astronomers calculate planetary orbits, they use gravitational models that predict positions precisely. They do not require a complete theory of quantum gravity. Prediction allows action. Explanation often follows later. This does not mean physics avoids deeper questions. It means those questions are approached cautiously. Explanations that cannot be tested remain provisional. Laws that cannot predict remain incomplete. There is gentle humour in the fact that some of the most philosophically unsettling theories ever developed are also among the most practically successful. Quantum theory raises profound questions about reality and measurement, yet it predicts experimental outcomes with astonishing precision. Relativity challenges common sense notions of time and space, yet it keeps navigation systems accurate to within meters. The universe does not seem to mind whether its behavior is intuitively satisfying. It responds only to consistency. Another important aspect of laws is their conditional nature. A law always carries an implicit phrase. Given these conditions, this behavior follows. Change the conditions, and the law may no longer apply. This is not weakness, it is clarity. A map is useful because it shows a specific region, not because it depicts the entire planet at once. When laws are treated as absolute and universal without qualification, confusion follows. When their scope is respected, they become powerful guides. This perspective also explains why different laws coexist. Mechanics describes motion at everyday scales. Thermodynamics describes energy flow in large systems. Quantum theory governs small scales. Relativity governs high speeds and strong gravity. None of these laws contradict one another. They overlap, approximate, and give way where appropriate. Seen this way, physics resembles a collection of lenses rather than a single picture. Each lens brings certain features into focus while leaving others blurred. Together, they offer a richer view than anyone could alone. There is also an important humility embedded in this framework. Physicists do not claim that current laws are final. History offers too many examples of confident completeness, followed by surprise. Instead, laws are treated as provisional summaries, always open to refinement. This openness is not uncertainty, it is discipline. A law that has survived countless tests earns trust, not because it is perfect, but because it has proven resilient. When new evidence appears, trust does not collapse, it adapts. This approach protects physics from dogma. Laws are respected, but never sacred. They are valued for what they do, not for what they claim to be. There's also a subtle shift in perspective that occurs when laws are understood this way. They stop feeling like external constraints and start feeling like descriptions of regularity. The universe is not restricted by laws. The laws are shaped by the universe. This reverses a common intuition. Instead of imagining reality conforming to equations, it becomes clear that equations are crafted to conform to reality. The fit is tested relentlessly. Where it fails, the equations change. This view also changes how disagreement is handled. Competing models are not philosophical rivals. They are hypotheses awaiting evidence. The one that predicts better survives. The rest are revised or set aside. This process has produced remarkable results. From predicting new particles to forecasting cosmic phenomena, physics has repeatedly shown that well-constructed laws can reach far beyond the conditions under which they were discovered. At the same time, this success invites reflection. If laws are models, what do they say about reality itself? Are they discovering something intrinsic or simply organizing observation efficiently? Does the universe possess laws, or does it simply behave in ways that can be summarized? Physics does not answer these questions definitively. It does not need to. What matters is that the laws work. They allow prediction, control, and understanding within defined limits. They allow technology to function. They allow exploration to proceed. They allow curiosity to be rewarded. As the focus begins to shift away from abstraction and back toward experience, this realization becomes grounding rather than unsettling. The laws of physics are not distant edicts. They are descriptions of the regularities that shape everyday life. They are present when objects fall, when heat flows, when light arrives, when time passes. They operate quietly, without needing acknowledgement. Understanding them is not a requirement for living within them. With this in mind, attention can return from models and frameworks to lived experience, to the way these laws express themselves in ordinary moments, to how a universe governed by consistent patterns feels from the inside. The story of physics does not end with equations. It continues in every step, every breath, and every interaction that unfolds according to rules that do not ask to be noticed. After moving through scales both vast and small, through forces, particles, symmetries, and models, everything quietly returns to where it began. Not in laboratories or equations, but in ordinary experience. A lawful universe does not announce itself. It shows up in small, dependable ways. A cup remains on a table rather than drifting upward. Morning light arrives when the sun rises. Sound travels through air. Heat moves from warm hands into cooler air. None of this feels remarkable, and that is precisely the point. reliability fades into the background. The laws of physics matter most when they do not demand attention. Everyday life depends on consistency. Floors support weight. Vehicles slow when brakes are applied. Food warms when heated. These outcomes are not negotiated anew each time. They follow patterns that have held for billions of years. The same principles governing distant galaxies quietly ensure that a glass does not fall sideways when released. There is comfort in this predictability. The universe does not improvise from moment to moment. It does not wake up undecided about how gravity should behave or whether energy should still be conserved. Even as conditions change, the underlying regularities remain steady. This steadiness allows planning, learning, memory, and trust. Consider how much of daily life assumes lawful behavior without conscious thought. Navigation systems rely on precise timing signals that account for relativistic effects. Buildings stand because materials behave consistently under stress. Medical imaging works because radiation interacts with matter in known ways. None of this requires awareness of the laws involved. The laws operate whether they are known or not. There is a gentle irony here. The more reliable the universe is, the less it draws attention to itself. This reliability also shapes expectations. When something unexpected happens, it stands out precisely because it violates what usually occurs. Surprise only exists against a backdrop of consistency. If everything were unpredictable, nothing would feel unusual. The laws of physics create that backdrop. They also create a sense of scale. The same rules apply whether walking across a room or watching planets move across the sky. Differences in size and speed change outcomes, but not the underlying principles. Motion, energy, and interaction follow the same logic everywhere. This universality quietly connects individual experience to the cosmos. When light enters a room, it follows the same electromagnetic rules that guide radiation from distant stars. When time passes on a wristwatch, it unfolds according to the same principles that shape the aging of galaxies. The distance between these scales is enormous, but the continuity is unbroken. There is something calming in realizing that nothing special is required to participate in this universe. No permission is needed, no knowledge is required. Everything already follows the same pattern simply by existing. Even complexity rests on simple foundations. Weather systems are intricate, yet they follow thermodynamic rules. Biological life is elaborate, yet it obeys chemistry and energy conservation. Thought itself depends on electrical signals traveling through neural networks according to physical law. Complexity emerges not by defying rules, but by building on them. This perspective softens the idea that laws are restrictive. They do not limit what can happen so much as they make anything stable enough to happen at all. Without reliable behavior, structures could not persist. Memory could not form. Life could not adapt. There is also a quiet kindness in the fact that the universe does not require constant supervision. Once conditions are set, behavior follows naturally. Objects do not need to be reminded to fall. Energy does not need encouragement to spread. Processes unfold without instruction. From a human point of view, this allows attention to shift elsewhere. Effort can be spent on meaning, creativity, and care, rather than on constantly managing basic reality. The laws of physics matter not because they are impressive, but because they are dependable. They are not experienced as equations, they are experienced as trust. Trust that the ground will be there. Trust that cause precedes effect. Trust that tomorrow will resemble today closely enough to be navigable. Even uncertainty fits into this picture. Quantum probability does not undermine reliability at human scales. It averages out, leaving a world that feels solid and predictable. The deeper layers fluctuate, but the surface remains calm. There is gentle humour in the fact that the universe can be wildly strange underneath and still present such a steady face. Beneath every step lies quantum uncertainty, relativistic geometry, and statistical behavior. Yet shoes remain on the floor. This layered structure allows wonder without anxiety. Strangeness exists, but it does not intrude. Mystery operates quietly, without disrupting breakfast or sleep. Living in a lawful universe also means living in a place where learning works. Experience accumulates, skills improve, patterns can be recognized and used, knowledge can be passed along. None of this would be possible if behavior shifted arbitrarily. The success of science itself is a consequence of this. Observation would be meaningless without repetition. Prediction would fail without consistency. Understanding would dissolve without regularity. Yet the universe does not feel rigid. Laws allow variation within bounds. Outcomes differ. Paths diverge. Systems evolve. The rules do not specify details. They constrain possibilities without dictating exact results. Within that space, creativity emerges. This balance between structure and freedom is what allows both order and novelty. Stars form, but no two are identical. Lives unfold, but no two follow the same course. The laws do not script events. They provide a stage on which events can occur. As attention settles back into ordinary experience, the vastness explored earlier does not disappear. It becomes quieter. The same laws that shape cosmic expansion and quantum behavior are present in every moment, simply doing their work without commentary. Understanding this does not require holding every concept in mind. Nothing needs to be remembered. The universe continues regardless. There's a particular calm in knowing that reality is not fragile, that it does not depend on belief or attention, that it does not change character when unobserved. The laws remain in place, quietly supporting everything. As this journey draws toward rest, what remains is not a conclusion, but a sense of continuity. The universe is lawful, not because it must be, but because it is. The patterns hold. The rules repeat. The background remains steady. Life unfolds within that steadiness. And while the laws of physics can be studied, questioned, refined, and reinterpreted, they are never distant. They are present in every breath, every step, every moment of stillness. Nothing needs to be done with this knowledge. It is enough to exist within it. Across everything explored, one quiet idea has remained steady. The universe behaves in reliable ways, not rigidly, not mechanically, but consistently enough that patterns can be noticed, trusted, and returned to. The laws of physics describe that consistency. They do not sit above reality like instructions waiting to be followed. They arise from observation, from noticing that when similar conditions repeat, similar outcomes tend to follow, from recognizing that motion behaves in familiar ways, that energy is accounted for, that time moves forward with a direction shaped by change, and that space itself responds gently to what it contains. This reliability is what allows the universe to feel stable. A predictable universe does not mean a boring one. It means a navigable one. It means that experience can accumulate. That memory makes sense. That cause and effect remain linked closely enough for understanding to grow. Without this steadiness, nothing could persist long enough to matter. The laws do not promise certainty in every detail. They do not specify exact outcomes in complex situations. Instead, they define boundaries. They say what is allowed, what is forbidden, and what tends to happen most often. Within those boundaries, variation unfolds freely. This balance between structure and openness is what allows both order and surprise. Throughout this journey, no final rule has claimed dominance. Each law has revealed its own limits. Classical motion gives way to relativity at high speeds. Relativity softens into quantum behavior at small scales. Quantum rules themselves resist simple interpretation. offering probabilities rather than certainties. None of this weakens the laws. It shows how carefully they are layered. Physics does not offer a single final sentence about reality. It offers a collection of reliable descriptions, each valid within its own domain. Together, they form a map rather than a declaration, a guide rather than a verdict. This is why continuity matters more than conclusion. The universe does not appear to be racing toward a final explanation. Each discovery opens space for the next question. Each refinement clarifies one region, while revealing another that remains unclear. The process does not stall, it deepens. There is reassurance in that. A universe that cannot be fully exhausted by explanation is not unstable. It is rich. It offers understanding without demanding closure. It allows curiosity without requiring resolution. The laws of physics do not insist on being memorized or mastered. They operate quietly whether or not they are understood. Gravity continues to hold. Energy continues to flow. Light continues to arrive. Time continues to pass. None of this depends on attention. This makes the laws easy to live with. They do not intrude. They do not fluctuate. They do not surprise without reason. They provide a steady background against which life unfolds. Even when events feel chaotic, the underlying structure remains intact. In moments of uncertainty, this steadiness matters. It means that while outcomes can vary, the framework does not dissolve. While details change, the foundations hold. The universe does not behave differently because it is observed differently. It remains itself. There is also something quietly human in the way laws are used. They are tools for understanding, not claims of ownership. They describe what has been seen so far as accurately as possible, with the understanding that tomorrow may add detail or nuance. They invite revision rather than resisting it. This openness is not weakness, it is resilience. A law that can be refined can survive new evidence. A model that can be adjusted can continue to serve. Physics endures not because it is final, but because it is flexible. Seen this way, the laws of physics are not distant abstractions. They are expressions of the universe's patience, its willingness to behave the same way long enough to be known. Everyday life unfolds inside that patience. Steps are taken without recalculating gravity. Conversations happen without checking the speed of sound. Rest comes without questioning whether time will still move forward. The laws hold quietly in the background, allowing attention to rest elsewhere. This is the calm gift of a lawful universe. It does not demand belief. It does not ask for acknowledgement. It simply continues. There is no need to carry every concept forward. No requirement to remember names, principles, or relationships. The universe does not test understanding. It does not reward comprehension with permission to exist. Everything already belongs. The same laws that shape stars and atoms are present here, now, doing their work without effort. They do not need to be solved. They do not need to be concluded. They only need to continue, and they do. As this exploration settles to a close, what remains is not an answer, but a sense of steadiness. The feeling that beneath complexity, beneath mystery, beneath even uncertainty, there is continuity, a universe that behaves in ways that can be trusted. That is enough. The rest can unfold slowly, one moment at a time,